Welcome to Math341. This is, I believe, lecture 11. And so what I wanted to do today is I wanted to just do a quick review over some of the stuff we've done, talk about variances and covariances. And the question is always how much detail to go into. The calculations are all pretty similar. And so I'm probably not going to go through all the calculations because it's in the book. If you have questions, talk to each other, talk to the TAs, talk to me. I want to use class time effectively. And so what I want to do instead is I want to give an example of why do we care about stuff like this and how easy is it to misuse what we're learning. And then I want to spend time writing another code. So I want to talk about how do you write a code to efficiently do a problem. And if there's a very specific problem that you want to solve and you are laser focused and that is all that you care about, then you can exploit things about that specific problem. And then all of a sudden, if later on your boss tells you, that's great, now can you do the following? If your code is not flexible, then you may have to go back to the beginning and it may be a completely new code. So it's an interesting question of when do you write things in great generality and when do you tailor things to the particular problem that you want to investigate? If you are writing a specific app that's going to be used for just a specific function, then tailor it to that and be as efficient as possible. But if you're in a situation where you could be asked a slew of questions, you want to think about how can I write things efficiently? And at the same time, have the flexibility I need later. So we talked about a deck of cards. If I only care about getting at least 2 queens and at least 2 kings, I'll assign the values of 10 to kings and 1 to queens and 0 to everything else. And it makes those problems very easy. But now if all of a sudden I cared about getting at least 2 queens, at least 2 kings, and at least 1 heart, now all of a sudden the problem is very difficult and I would have to redo things. So again, it's a nice challenge to be thinking between those two. The application I will be giving is to portfolio. I don't think we're going to have time to get to differentiating identities today because I really want to do some coding and talk about ways to do things. So I think differentiating identities is chapter 11. You should have already started to read this. As always, I'm trying to make sure that the homework that is due is on material that we've covered quite a while ago. That doesn't mean you shouldn't start doing homework that's not due for a while. I want you to start doing the homework as soon as possible. This just gives you plenty of time. So if you have a meeting or if you have a meet or you have some travel to do or a job interview and you have a busy week, you've got some flexibility and slack in that. But please build up a strategic reserve. I know spring break is coming. It's great to have a time to recharge, but it's also a good opportunity to put a little bit in the bank. And so, it's a nice question to decide how much time do you want to spend during spring break to just make the rest of your semester more manageable. As I've said before, I try to do more work in the beginning of the semester than the end of the semester because I know a lot of my colleagues are the other way around, so that this way things will fit a little bit better. The big item today is the power of independence. When things are independent, calculations are often much easier to do. All right, so let me just quickly review. And the main reason for having some of these slides is just to have them, again, in your notes in a very handy way. This is the method of the cumulative distribution function. This is just, straight from the book and just enumerating what's going on and how we can convert from from being able to generate one random variable to being able to generate another random variable. There's a couple of technical conditions to be careful about. We need to have functions that are invertible. We need the derivative not to be 0. And so for the most part, in the change of variables we're doing, this is not a problem. If I want to replace x with x squared, that's not a problem if x is a non-negative variable. But if x goes from -1 to 1, now all of a sudden that's a little bit tricky. If I now give you the value of 1/4, is that coming from x equals -1/2 or x equals 1/2? Sometimes what you need to do in a situation like that is you break things up into different cases. If it's between -1 and 0, I will use this change of variables. If it's between 0 and 1, I will use this change of variables. Sometimes the conditions are violated, but they're violated weakly and we can deal with it. If you have done polar coordinates, you have done spherical coordinates. You may not remember, but you've done them. And the transformation is not one-to-one everywhere. If you look at what's going on to the origin, that's the radius is 0, but the angles could be anything from 0 to the maximum value. So you don't have a unique inverse at that one point. Turns out it's not a big deal. The way those coordinate transformations work, one place where things aren't one-to-one is okay. But again, I just want you to be aware of all these different conditions. The next thing is the convolution. And we will see a lot of this later in the semester when we get to studying the central limit theorem. It is a machine that allows us to write down the density for a sum of random variables that are independent in terms of the densities of the random variables. This is exactly what we would like. In an ideal world, those integrals would be easy to do, and we would have a nice closed form answer. Not happening. We saw, and this is why I took the time to write it, what happens when you just add the uniform random variable to itself 4 times, 8 times. We saw how horrible it became. And that's a uniform. That's the constant function. Imagine how much worse it's going to be in general. So basically, it's in principle, this is fine. In practice, this is not tractable. But what we could do is maybe approximate the integral. This is going to be a function of z. Maybe we can approximate it. And if we have more and more terms, if we have x1 plus x2 plus x3 plus x4, the more terms we have, the more we can approximate things. Think of it as trying to know the US debt, and unfortunately, you can only get it to within $15. Not a big deal. The debt is so big that being off by 15 is insignificant. When we're trying to estimate quantities like this, we don't have to be perfect. We just have to be close. And for many applications, we need to quantify what does close mean? How close are we? All right. And then the convolution has a lot of nice properties. The convolution of two functions, it doesn't depend on the order, it's commutative. If these functions are coming from probability distributions, it's clear because x plus y is the same as y plus x. But this is actually true in greater generality, and I've urged you to try to prove that. All right, the next is just the statement of the mean and the variance. Again, this is all review. I know some people take a little bit of time to get here because the campus is not a point, and I know people sometimes have classes here, so trying to review just a little bit right now in the beginning. So the definition of the mean is the expected value of x. So it's the sum of x times f of x. If we have a continuous random variable, of course, you replace the sums with integrals. And the hope is that these sums and integrals exist. We have the technical caveat that the integral or the sum of the absolute value of x times the probability density must be finite. Why don't I have the probability density under the absolute value sign? Why is it just the x? Why isn't the probability density under the absolute value? Yeah, it's always greater than equal to 0. I could put it under the absolute value if I wanted to, but there's no need because the probability density is non-negative. All right, the variance is the integral or the sum of x minus the mean squared. And so this talks about how spread out something is. If all the mass is concentrated at the mean, then the variance would be 0. And the variance has units the square of the units of what you're studying. So if I'm studying something in meters, the variance has units of meters squared. If I want to talk about fluctuations, I want to have the same units. So you take the square root, which is the standard deviation. Right? When you see a notation with a square as part of its notation, part of its definition, that should be a hint that you want to take the square root. For some things, the variance is the natural quantity to look at. For other things, the standard deviation is. In terms of computation, it's a nice straightforward exercise, and I urge you to do this or read the book, that the expected value of x squared minus the square of the expected value of x is another way of calculating the variance. That's the same as calculating the expected value of the quantity x minus mean squared. So we have two different ways to compute the variance. What's nice is it's very easy to calculate the expected value of x squared. That's just another sum or another integral to do. And that might be important later today when we're doing some coding. This also tells you that order matters. The expected value of x squared, so usually the expected value of x squared does not equal the square of the expected value. Order matters. If I square my random variable and then take the expected value, that's not the same as taking the expected value and squaring it. If that were the case, then everything would have variance 0, right? And there's actually no need to have more than one of you take the final or the midterm, because there'd be no variance, right? Any one of you would be fine. So it's nice to just, get some quick senses of, what would be the consequences. If you think of x as a variable that has mean 0, well, if I look at x squared, that should almost certainly not have an expected value of 0. The only way that would happen is if it's always 0. So I don't expect the expected value of x squared to equal the square of the expected value of x. Okay. To introduce some notation, I think most of you have seen covariance before. If you think about how it's named, there's two parts to the word covariance, and they are co, and in a shocker, variance, right? So it seems like it should be related to variance, and the co means it's related to how things are varying together. So the variance of x and y together. So we define the covariance as the expected value of x minus its mean times y minus its mean. And actually, I really should have had colon equals, because this is a definition. This is how we're defining the covariance. This is good notation. It has an x and a y. I'm using the sigma, so this makes me think of things like standard deviation and variance. Should I have a sigma squared? I don't know. What would be an interesting choice for y? X. So if you take y equals x, the covariance of x and x becomes the variance of x. So when you look at the final formula, the variance of x is the sum of the variances of the xi's plus twice the covariances. Well, I could really just write it as just the sum of covariances, because the covariance of xi with xi is just the variance of xi. We isolate it like this because in many situations, the covariance terms are 0 if I is not equal to j. And so it's convenient to write it like this. You always want to think about what's going on and look at things carefully. If you look very carefully, the middle inequality is different than the others. The middle is just a strictly less than, and the others are less than or equal to. And the reason is if I equal j, then that would be the variance terms. That's what all of this stuff over here is. That's coming from I equals j. And the 2 over here is coming from I less than j. Because really we should look, when we expand things out, we have the covariance of x1 and x5 and the covariance of x5 and x1. But you can see that the covariance of xy is the same as the covariance of yx. So to simplify our life, let's just compute half of them and double. But the problem is we can't just double everything because the diagonal terms when I equals j, those only happen once. The other terms happen twice. That's another reason why we like to split off the variance over here and then have the sum of the covariances elsewhere. So this formula just comes from splitting things out and expanding. Okay, and then we've talked a little bit about some of these before. We'll get to a more challenging one in a moment. Just for explicitness and just to have this in our records, this is calculating the mean and the variance of a Bernoulli distribution. So we've done this before, and this is a very straightforward calculation. It takes on the value of 1 with probability p, 0 with the probability 1 minus p. We calculate that the mean is p, and we calculate that the variance is p times 1 minus p. It's probably not bad to have this memorized. This occurs so many times. You should know that if I have a Bernoulli random variable, its mean is p, its variance is p times 1 minus p. If you forget it, not a big deal. You can calculate it quickly. You can look it up pretty quickly, but it's used so many times, it's worth having. The calculations here are pretty straightforward because it only takes on 2 values, and those values are 0 and 1. What's nice is if you try to calculate any moments, it really doesn't change. All of the moments are going to be p. Every moment is p. So this is a very special distribution. When it's sometimes called a binary indicator variable, it only takes on the values 0 and 1. And what's nice about that is x is the same as x squared is the same as x cubed. Right. So we've done this calculation before. This is going to be the building block to understanding binomial distributions, which we've seen before. And then we will see later how to do them better. Right. The next is some straightforward integration results, which you should try to prove. So if x is a random variable with mean mu of x and variance sigma of x squared, and a and b are constants, we can consider a new random variable y equals ax plus b. This is a linear rescaling. And it turns out that the mean of y is a times the mean of x plus b, and the variance of y is a squared times the variance of x. This is very reasonable. If I take my random variable and add 15 to everything, what should happen to the mean? Goes up by 15. That's what the plus b does. It just shifts the mean up by 15. Makes sense. If I shift every score by 15, does that change the fluctuations about the mean? No, because it's x minus the mean. If I shift x up by 15 and I shift the mean up by 15, then I don't change the difference. That's why there's no b dependence in the variance of y. So again, whenever you see an equation, is this reasonable? Yes, I don't expect any dependence. The next thing is, if I multiply all values of my random variable by 5, the mean should go up by 5. And that's where we have the a times the mean. Again, makes perfect sense. What about the variance? Well, variance is we're squaring things. So if I multiply everything by 5, then I change all of the x minus mu squareds by 5 squared. And so the variance changes by 5 squared. Can somebody tell me why it would be absurd if instead of a squared, I had it was just a? Why is there no way that could be right? So one thing is, it feels like it should depend on a squared because, if I multiply by 5, I'm changing all the squares by 5 squared. But there's another more fundamental reason why it can't just be a. So think of extreme cases, yes. Yes, and in fact, -1 is exactly the number I was thinking of. If you take a equals -1, it would now give you the variance as negative. If you can sum a bunch of squares of real numbers and get a negative number, I'm impressed. Right? If you square real numbers, they're non-negative. So their sum can't be negative. So I know immediately that the variance can't depend on a times. And so really, if you think about it, the sign shouldn't change the fluctuations. The fluctuations are measuring how things are distributed about the mean. The sign just changes which side it's on. It doesn't change the amount it's fluctuating. So again, I urge you to do the calculations. They're in the book, but you should try to prove it yourself. And then, I've mentioned before, and this just comes from expanding out the definition, this is extremely valuable. One way to compute the variance is to look at the square of x, take its expected value, and then subtract off the square of the expected value of x. How many of you remember directional derivatives from multivariable calculus? You want to know how fast is the function changing in a given direction. There is a definition of what the directional derivative is. And to compute it, it's just take the gradient and dot it with the direction. Okay, much easier to just take the gradient, dot it with the direction, than to go back to the definition. So from a computational perspective, we don't want to go back to definitions. We want to use simple formulas. For a lot of things, it's much easier to calculate the variance as follows. Okay, so here's a big one. If x and y are independent random variables, then the expected value of the product is the product of the expected values. And a particularly important case is the expected value of x minus its mean times y minus its mean is 0. The first thing is that if x and y are independent, if I shift x, it doesn't change whether or not they're independent. So what you could do is you could first say x and y are independent. That implies x minus its mean and y are independent. And then that implies x minus its mean, y minus its mean are independent. So when you go through the calculation, if I just shift x, if y gave me no information about x before, it's not going to give me any information if I just add a fixed amount to x. And so I can just go through it in shifts of one random variable at a time. This is extremely useful. The expected value of a product is the product of the expected values. Is this always true? Give me an example when it's not true. So when is the expected value of a product not the product of the expected values? Yeah, when y is x, the only way that it could be true is if x is always 0, or maybe always 1, or maybe always -1, something like that. In general, if y equals x, they're dependent. And take any random variable that has mean 0. So maybe x is 1/2 the time and -1/2 the time. Then if I tried that, the expected value of x is 0, but the expected value of x squared is 1. So the key word here is independent. Or unfortunately, I circled 2 words. I circled them really nicely, though. So the 2 key words are independent. Right? So if they are independent, then this is true. If they're not independent, it may be true. It turns out it's not always true, but it is possible that I could have 2 dependent random variables such that this is true. So as a nice exercise, find 2 random variables, I'll make this extra credit, that are not independent, but the expected value of the product is the product of the expected values. Okay? So again, you've got to be very careful which way things goes. I'm not saying that this only holds when they're independent. I'm saying if they're independent, this holds. And if this holds, life is good. What would the covariance be if x and y are independent? 0, which makes sense. The covariance is kind of measuring how they vary together. Well, if they're independent, there's really no connection. All right, so the question is, how rigorously do we prove this? So proof. Let's let z equal x times y. The expected value of z would be the integral minus infinity to infinity, integral minus infinity to infinity, x times y times the density function of xy dx dy. And I'll put on the variable names. All right, now, because the random variables are independent, what do you know about the joint density function? So what's true about the joint density function if they're independent? How can I relate that to the density functions of x and y? I'm sorry? Not plus, times. So as independent, the joint density function of x and y is the product of the density functions of x and y. That is not true in general. But if they're independent, it's true, and it makes things really nice. So now we get the expected value of xy is going to be the integral y goes from minus infinity to infinity of y fy of y dy, integral x goes from minus infinity to infinity x fx of x dx. And the first one here is just the expected value of y, so I guess I wrote them in the wrong order, and this one is just the expected value of x. And so the proof is actually not too bad. Whenever you're proving something, you should be looking at the conditions. The conditions are probably used. It's possible that you do not need to use all the conditions. Will I ever knowingly give you an exam question with not enough information to solve? No. Will I ever knowingly give you an exam question with more information than you need? Almost surely. Right? And there can be red herrings. In life, you don't necessarily know what's useful for the problem. In lower level classes, it's much easier. I think I've used this example before. You're doing calculus, section 3.2 is on the chain rule. What should you use to do the homework problems? Not that hard. You're doing multivariable calculus, you've just done spherical coordinates. Gee, I wonder what might be useful to solve this integral over the sphere, right? It's kind of hard to hide what to do. As you get further and further along, it's much harder to figure out what to try. So you need to focus on keywords. What's the key word to focus on here? Yeah, independent. And I'll try to just circle just independent that time, right? That's the key word. And as soon as you know that that's the key word, then you ask, what do I know because they're independent? And you just list all the things you know about independence. Well, I know if they're independent, then the probability density function factors as the product of the density functions of each one. Let me try to use that somewhere in the proof. Sometimes you can prove a special case of something, and that proof is not going to necessarily generalize well. So you have to be a little bit careful, but you should always be thinking, what do I get? Okay. So now for the binomial distribution, we actually did this before. And so we could write down what's the probability if we have a coin with probability P of heads, and we do n tosses that are independent. What's the probability we get exactly k heads? That was n choose k, p to the k, 1 minus p to the n minus k, if k is an integer between 0 and n, and 0 otherwise. And then we could try to calculate the expected value directly. And we saw how painful that was. We could also try to calculate it by saying, well, the number of heads is just a sum of a sum of random variables of what's going on for the first toss, the second toss, all the way up to the nth toss. And so the total number of heads, x, is the sum of n independent, identically distributed random variables. They're all Bernoulli probability P of success. So the expected value of the sum is the sum of the expected values. That gives us NP. And the variance of the sum is the sum of the variances. Why is the variance the sum of the variances? It's because they're independent. So the variance of the sum is the sum of the variances as independent. And this is one of the reasons why the variance is such a nice thing to look at. Do you think the standard deviation of a sum is the sum of the standard deviations? No. Right? If we have, sigma squared is sigma 1 squared plus sigma 2 squared, does that imply sigma equals sigma 1 plus sigma 2? No. I have seen lower level classes where students do such algebra where they divide the exponents on each side by 2 and cancel. You can't do that. This gives you a sense of why the standard deviation, in some senses, is not necessarily as good of a statistic as the variance. The variance of a sum is the sum of the variances. That's nice. Okay. So let's look a little bit. So your big theorem, 962, the mean of a sum is the sum of the means. The variance of a sum of independent random variables is the sum of the variances. And if they're all the same, then the mean is just n times any of the means, and the variance is just n times any of the standard deviations. What is the extra condition between the means and the variances? So there's a condition for the variance result that's not on the mean result. Independence, right? So we keep seeing this again and again and again. When things are independent, we have some additional facts about the variances. If we do not have independence, we have to include all those covariance terms. I've done some research with small students where we have some annoyances because of covariance terms. And sometimes what we can do for certain problems is it's just enough to bound the dependence. If the dependence isn't too bad, then the effect is actually quite small and we can just ignore it. A lot of times people make mistakes on covariances. This is the cause of the financial collapse, the Great Recession in 08, 09, is people assumed certain things were more independent than they actually were, and they used various math models that assumed independence, or they assumed dependence only to a certain level, and it was actually far more dependent than it was. And this is the talk I had encouraged some of you to go to, right? Let's look at the proof of the variance case. There are several ways to do the proof. One is roll up our sleeves and let's just do lots of calculations. The other is the shampoo method. Let's try to prove it in a special case and then generalize from that. I like the shampoo method. It keeps the notation a little simpler. It keeps things a little bit smaller. So imagine no for two sums, or two terms. So let's look at the variance of x1 plus x2 plus x3. And I'm going to group them by putting x1 and x2 together. So if we know the result holds for the variance of a sum of two terms is the sum of the two variances, this then becomes the variance of x1 plus x2 plus the variance of x3. But what's true about the variance of x1 plus x2? Good, so the variance of x1 plus x2 is? Right, so I'll put that in parentheses, x1 plus variance of x2 plus the variance of x3. And now let's just drop all the parentheses, and it's just variance of x1 plus variance of x2 plus variance of x3. This is a really good concept to get down. What it basically says is, I don't need to deal with the general case and the painful notation that arises. It's enough to do two independent random variables. Because if I can do two, I can do three by grouping two of them together, and now again I have two. Now if you give me four, I group the first three together. And I can keep going like that. Technically, this would be a proof by induction. And fortunately, we spent part of a class putting that in our wheelbarrow of knowledge, so we can now use proof by induction to do this rigorously. But the idea is I can break this up into a simpler case, do that simpler case, and then just extrapolate by induction to everything, as long as the sum is finite. I cannot deal with an infinite sum, and I know some of you are challenging me with infinities. So we have to be a little bit careful, but as long as it's only finite, we're okay. Most people are not able to flip infinitely many coins. This is not a real restriction in the problems we will be looking at. So we just have to study the variance of a sum. Okay, so let's look at the proof. Now the next thing is we can choose some notation. We can do x1 and x2, or we could do x and y. Which would you prefer to do? Both are defensible. X and y. So let's do x and y. Okay, so we want to look at the variance of x plus y. What is that going to be? That's going to be the expected value of x plus y minus the mean of x plus the mean of y. And we square that. Okay, so this is the expected value. And now I'm going to group things. What should I group with x? I've got xy minus mu x minus mu y. What should be grouped with x? Yeah, let's have the mean of x next to x, and let's have the mean of y next to y. But I have to square this whole thing and then take the expected value. Okay, so this is the expected value of x minus mu of x squared plus twice expected x minus mu of x, y minus mu of y, plus y minus mu y squared. If I wanted to, could I write this as an integral with a probability density function? Sure. I don't want to. It's much better, it's much easier to just use the concise notation of expected value. What's the expected value of a sum? The sum of the expected values. So this is now just, I could save time by just cutting and pasting, but since you have to write as well, I don't want to do things too quickly. It's just the expected value of x minus mu of x squared. Now, the expected value of twice something is just twice the expected value. So it's going to just be twice the expected value. Now, what's the expected value of that product? So what's the expected value of x minus mu x times y minus mu y? It is the covariance, but in this particular case, what is the expected value of that product? The product of the expected values. Why is it the product of the expected values? Because they're independent. So this is the same as the expected value of x minus mu of x times the expected value of y minus mu y plus the expected value of y minus mu y squared. And this is because independent. Okay, what is the expected value of x minus its mean squared? The variance. Which variance? The variance of x. What is the expected value of x minus its mean? Zero. So as an aside, I don't know if we ever actually proved this, so I'll just do a quick lemma. The expected value of x minus its mean equals 0. Proof. It equals the expected value of x minus the expected value of the mean of x. What is the expected value of x? The mean of x. What's the expected value of any constant? That constant. So you get 0. So I don't think we ever actually proved this directly, but the expected value of x minus its mean. Think of it this way. You have a class where the average is 95. I subtract 95 from every score. What's the new average? 0. So again, whenever possible, you want to tell a story. If you think about the mean value theorem, if you are traveling and your average speed is 50 miles per hour, at some point you must have been traveling exactly 50 miles per hour. Well, if you're always traveling below 50, how could your average be 50? If you're always traveling above 50, how could your average be 50? So at some point your average is below 50, some point your average is above 50. By the intermediate value theorem, there must be some point where you're exactly 50. So whenever you can tell a story, tell a story. So over here we get variance of x plus 0 plus the variance of y, and that's what we needed to prove. So the variance of a sum is the sum of the variances as long as the covariance terms vanish. Notice that the variance of a sum can be the sum of the variances even when they're not independent. As long as the covariances sum to 0, it's true. What's the easiest way to ensure that the covariances sum to 0? Making them the same, making that same value. So what's the easiest way to make sure a sum of terms equals 0? Each term should be. So you want to make sure that a sum is 0. You said you want all the terms to be the same. What should that common value be? To make sure that the sum is 0, each term should just be. Should just be 0. If all the covariances are 0, then clearly the sum of the covariances is 0. It's possible that the covariances could sum to zero without them all being zero. That's much harder to find. So fortunately, there are many situations where the covariances will be zero, and then formulas will simplify. We call this the academic classroom, the Ivy Halls. When you go out into the real world, no. Then you have to deal with covariances and the fact that it's extremely important to incorporate these. But let's start off with some easier stuff. All right. So then, the formula mentioned before, if x and y are random variables, the covariance, as we've said multiple times, is defined as the expected value of x minus its mean times y minus its mean. The covariance of x with x is the variance of x. And then if we let x be the sum of the xi's, then the variance of the sum is the sum of the variances plus twice the covariance terms. And we count from I strictly less than j. So that's what the factor of 2 does. It counts I less than j and I greater than j, but allows us to just simplify our calculations a little bit. Going through the calculation, it turns out that the covariance of x minus mu, the expected value of x minus mu, y minus mu is the same as the expected value of the product minus the product of the means. And again, we just keep using linearity of expectation. So the key ingredient in everything we do, it's what we just did a few moments ago. When we did the proof here, we used linearity of expectation. It is amazing how many things fall from linearity of expectation. Okay, so here is a fun problem. Is anybody here a double major or majoring in economics? Okay, excellent. So a couple of, okay, I'm not sure I'd say it's excellent to major in economics, but here is an example you should be aware of, portfolio theory. So what is your goal? And I'm going to put you econ students on the spot in designing a portfolio. What are you trying to do? Maximize your return. Minimize risk. So there's two very natural objectives. And depending on where you are in life, you might weigh those two objectives very differently. If you are young, can you afford maybe more risk? Yeah, you've got a lot of years left. I'm not going to risk asking what you consider old based on my age right now, but if you're old, you may not be thrilled at a huge amount of risk because you don't have as much time to recoup. And you may now be on fixed income drawing down your reserves. So all of a sudden, so it was interesting during the Great Recession, schools like Williams had 50% of its operating budget coming from revenue generated by the endowment. So when the endowment plummets 50%, that's a huge hit to the operating budget. There were other schools that had only 10% of their operating costs coming from their endowment. So when the endowment plunged, it didn't really affect them that much, which is the better strategy. You need more information. If you have a lot of years with high return, we always focus on the bad decision we make. Oh, damn it, that didn't work out. Yes, I lost money on this, and I made money on 15 other items, and I made so much money, it more than covers for that. Can you just focus on all the good things that happen to you and not fixate on the one bad call? No. So many of us, we fixate on that one bad decision. I shouldn't have done this. Yes, correct. You shouldn't have done that, but look at all the things you did right. And so for some things, it's actually not a bad strategy to occasionally have calamities happen. Because if you can make enough money in the intervening time, it's actually worth taking a little bit of a hit. Okay? So the question is, what's the best strategy for a university or a college? They're going to be around for a while. They might be willing to have more of a risk because they can afford a few bad years. So let's consider the situation where we have two stocks, X1 and X2. They both cost $1 per share, and they both have the same average return of 3. And they'll both have a variance of 2. And we want to build a portfolio that makes as much money as possible with as little risk as possible. So I realize these are competing influences. How should we do this? Well, let's assume let's let 0 be less than equal. Oops, let's use blue. No, we'll use green for economics. 0 less than equal to W, less than equal to 1. Invest W% in X1 and 1 minus W% in X2. So our portfolio is this nice weighted sum. What's the expected value of X? So how would we calculate the expected value of this weighted portfolio? Sum of the expected value. So it's the expected value of Wx1 plus the expected value of 1 minus Wx2. And so I'm just going through it very slowly. Now, what's the expected value of W times X1? W times the expected value of X1 because it's constant. So this would then just be W times the expected value of X1 plus 1 minus W times the expected value of X2, which is just W times, what did I say it was, $3 plus 1 minus W times $3, which equals $3. So if I just, yes. The expected value is $3, but my profit would be then $2. Okay. Yes. So if I look at the expected return is $3, the expected cost is $1. If they had different costs, then I would have to take that into account as well. Right now, I'm saying I have two things that I can investigate, that I can invest in. They both have the same return. They both have the same variance. I'm going to assume that they are what? Independent. And I knew that word had to be somewhere in here. There's the word, independent, right? Big assumption. From this point of view, if I only care about the expected value, does it matter how I allocate between the two resources? No, I'm indifferent. No matter what W you give me, my expected return is 3. Let's look at the variance. I'll switch to red for warning. So the variance of X is the variance of W X1 plus 1 minus W X2. What's the variance of a sum? Sum of their variances. And so that's my first quantity, that's my second quantity. So this is going to be the variance of W X1 plus the variance of 1 minus W times X2. Okay, what's the variance of a constant times X1? The constant squared. And this is good because it's going to be a non-negative number. So I'm going to get W squared variance of X1 plus 1 minus W squared, the variance of X2. Well, both of them have the same variance, which I said was 2. So it's going to be W squared plus 1 minus W. Oops, sorry. I put the square in the wrong spot. My apologies. It's 1 minus W quantity squared times 2. Actually, there's a small typo. Can it have a variance of $2?
The unit.
Yeah, that's the wrong unit, right? I should really say, standard deviation of $2 or something like that. We'll ignore that right now, okay? But so now, what W should I choose? Does it matter which W I choose? So variance of X is W squared plus 1 minus W squared times 2, find W to minimize. Now, if we minimize the variance, we're lowering our risk of getting a small return. Is that good? What are we giving up? Getting a high return. Anybody ever heard the word Panstaffel? Cultural extra credit. It's one of my favorite words. There ain't no such thing as a free lunch, right? There's trade-offs, and you have to decide, is this trade-off worth it? We can minimize our risk of having a low return, but at the same time, that also minimizes our chance of a high return. For a lot of things, I would much rather have something that's known. I have done some work in local government for finances between multiple towns in a regional school district. And one of the things that can be a real challenge is budgets having huge fluctuations from one year to the next. Town managers like to have some consistency. They like to know what's coming. And so I'm happy to talk about that during recording malfunctions. As to what do you do? What formulas do you want? What trade-offs are you willing to do? So how do you think we would find the value of W that's best? How could we do it? Take derivative, and what else?
Oh, use move from
No, we can do this. I'll try to do this. Is it showing? Okay. So, is it no longer? Okay. So let's see. Is it showing? Okay. It's not projecting. Oh well. The video. Okay. It's showing on my computer here, but it's not showing here. All right. Let me try one more time, and then you will give up on this. All right. So you said take the derivative and set the derivative equal to 0. Okay. Okay, so I want you to tell me where you think I am traveling fastest. Okay. And then, so hopefully we'll, is it showing now? No, it has to go. Ready? So where am I traveling fastest? So wasn't my derivative a 0? No. I'm really glad to be doing this in a classroom that has a door with a handle that you can push open. It is much more pleasant than other rooms where I have done this. So it's not where my derivative is 0. What do you have to remember as well? Boundaries, right? There was a problem earlier in the semester where I think we had marble jars, and you have to remember to check the boundaries as well. I think a lot of you was forgetting to check the boundaries initially. And so what we need to do here is let's let f of w equal w squared plus 1 minus w squared. Find critical points and endpoints. So f prime of w is going to be 2w plus 2 times 1 minus w times -1. So f prime of w equals 0 implies w equals 1/2. I'll let you do the algebra. So f of 1/2 is going to be 1/4 plus 1 1/4 equals 1/2. F of 0 equals F of 1 equals 1. Minimum is at W equals 1/2. The other thing is you can think about this as it's clearly two parabolas. It's balanced in 1/2. You can plot it. You can actually decrease the variance by investing. So if independent can decrease variance by a combination. And then of course, yes.
I realized I think I would have done this. I was wondering what I said. How should I say it differently? How should I say it differently? If this instead of this.
Are you talking about finding the minimum or?
Yes.
So the way you find a minimum of a differentiable function is the candidates are the critical points and the endpoints.
Yes.
And so we then find the critical points, we find the endpoints, and we evaluate the function at all of them, and we just see where's it largest, where's it smallest. And so when we do this, we see that at the critical point, W equals 1/2, we get a value of 1/2 of the function. At the two endpoints, 0 and 1, we get a value of 1. So the smallest value for my function is at the critical point 1/2. So for this problem, the critical point is the minimum.
I see. So I should say critical point plus endpoint then check.
Correct. So you have to make sure you check all the candidates. So just because something is a candidate doesn't mean that it is realized there. So for example, if I give you f of x is x cubed, f prime of x is 3x squared, so critical points are just x equals 0. And if I look at, say, -1 less than equal to x less than equal to 1, if I plot my function, it's going to look something like this. So the critical point is not going to be a maximum or minimum. And the problem is the second derivative is 0 at x equals 0. Need to look at the third derivative at 0. And that's what's causing the problem. So just because you have a critical point doesn't mean it has a maximum or minimum there. Okay. So what I want to do now, I will just state on the slide here the method of differentiating identities, that basically if we have some relation involving some parameters, what we would love to do is take derivatives with respect to the parameters and move it through the sum, through the integral, and hit the right-hand side, and use that to extract formulas. We're going to spend a lot of time next week seeing just how much we can do from this. It's amazing how many things this solves. We will be able to calculate very difficult expected values trivially if we have these equalities to begin with. And so, again, it's whenever you have an equality in mathematics, you celebrate. It's a lot of work to prove an equality. And then wouldn't it be wonderful if you could generate infinitely many new equalities from a given equality? That's what this method does, is it creates new inequalities. Okay, what I want to do now is I want to code the crackerjack box problem. And so rather than actually coding it, I'll talk about it first. And then if there's time, I'll actually do the coding. So for the crackerjack problem, what do we have? So crackerjack toy problem. We have T toys, each box independent of others, each toy equally likely in any box. How many boxes to open till we see each toy? So we need to write some code to do this. So how do you want to store things? How do you want to calculate things? So the first question is, am I asking you to create a general code to handle a wide variety of problems, or a specific code, and this is the only thing I care about? It's always better to have a general code, but in this case, am I asking you for a general code, or is there a specific problem I want you to solve? This is a very specific problem. I can exploit properties of this. I could write a general code where at the end you could ask maybe, not only do I want to know how many boxes, I might want to know how many times did the most popular toy get chosen? Do I care about that right now? No, I only care about how many boxes. So I'm throwing away a lot of information. I'll assume nobody's ever seen the Zorro movie with Antonio Banderas. There's beautiful scene when somebody wants revenge and he's being trained by Zorro, and Zorro says, "This circle is your life right now. Until I tell you otherwise, nothing exists outside this circle. He exists. I want to kill him." No, he doesn't. Until I say so, nothing exists outside your training here and now. So right now, we only care about solving this problem. It might be nice to answer questions such as, how frequently was the most popular toy chosen? But I only care about this. So I open a box and I record what I got. I open a box, I record what I got. So how do I store the results? How do you think I should do this?
We need to keep track of what we've seen so far. So we could either have some sort of set structure, or we could have like that trick with like 1, 10, 100, and then just keep a sum that we have and let's check if we've seen something right.
Okay, so we could do a set structure. Open box. If not in set, add to set. Keep doing till set of size t. We could do the trick. The boxes are 1, 10, 100, ... Keep track of sum. But if we're doing that, we have to know whether or not we've already seen that number.
But we could like say we pick up 100 and our sum is 111, mod by 100.
Well, if you mod by 100, you won't know if you had the 100 or not. You would have to mod by 1,000 and then see if that's 100, if it's more than 100. So you could do, can do with mod games to see if have 100 mod by 1,000 and see if at least 100. So there are ways to do it like that. You could have an array and maybe, toy k equals 1, or toy k is increased if get toy k, and see if all are positive, if the product is positive. So this is actually not a bad way to do things, because if we do it like this, if I then ask you later, how popular was each toy, I now have that information stored. Right? Another way we could do this is let T max be the largest toy number seen. Initially, we've seen nothing. We open a box. Do we see a new toy? Without loss of generality, what's the first toy we see? Well, we see one. Okay. Without loss of generality, first toy seen is 1. So T max equals 1 now. Keep opening boxes until you see something greater than 1. Open boxes till see something greater than 1. And what happens if you now see something greater than 1? Let's say the first box you open is 1, then you open another box and it's 1, and then it's 1, and then it's 1, and then it's 5. Now what does T max become? No. What should T max become now? Make it 2. Right? You open it up and you see it. The first new thing you see, let's just call that price 2. Call whatever you see price 2. Right? Set T max equal to 2. Open boxes till see something greater than 2. Yes.
But this doesn't work if different toys have different populations in boxes, right?
We have assumed all toys equally likely. Yes. And so again, solving a very specific problem.
Maybe I'm just not following what T max is, but you said if we got toy 5, we said it equal to 2. We saw toy 5 again.
No, because if we see toy 5, we're going to just renumber in our mind and now consider toy 5 the second toy.
Okay. So we also keep track of that.
No, because it doesn't matter. So now we just change toy 5 to be toy 2 and toy 2 to be toy 5. We're going to choose numbers randomly from 1 to t. And you choose numbers randomly from 1 to t. So maybe we got 1, 1, 1, 1, 1, 5. So now I've seen 2 toys. I should be choosing numbers now from 1 to t, and it's new if it's not 1 or 5. But that's equivalent to choosing numbers from 1 to t, and if it's new if it's not 1 or 2. It's the same probability. So I'm just relabeling.
We're just going to increment until T max.
Yes. So we open boxes until we see something greater than 2. Call that toy 3. Now set T max equal to 3. And so I think this is a really nice, concise way to do it. I don't have to worry about mods. I don't have to worry about storing things in arrays. What is the probability? I can calculate all these probabilities without any trouble. And so yes.
We have to also increment how many toys.
So every time we do this, we would increase that counter by 1. Yes. Every time open a box, increase counter by 1. And so now we would just keep doing, do until T max equals T. And that will give us how long it took in this random process. And then we can store the result. And then if we wanted to find the average of doing this many times, you would just have maybe total count equals total count plus counter, and then divide by number of iterations to get average. And so we can now do this very concisely. What if I wanted to calculate the variance? Would I be screwed now if I wanted the variance? How would I get the variance? So just variance total count equals variance total count plus counter squared. And I would just have a running sum for that. And I would have my running sum for x. I'd have my running sum for x squared. I could save all these in an array. I could have an array of going from, say, maybe t to t squared, and just keep track of how many times it took exactly that many boxes. And if I did that, then if you ask me some other questions later on, it could be useful. You know, if you want the kurtosis, if you want the skewness, I could answer those. I couldn't answer which toy was most popular and by how much. I can't answer which toy was least popular and by how much. Well, it's what are you trying to solve? If you only care about a specific problem, we can often make the code a little bit easier, a little bit more efficient. But then if you have to change things, now you have to go all the way back to the drawing board. So if you're trying to run this at a very high level, every little bit of efficiency you can do is great.
What is total count? Why are we adding counter, which we're already?
Well, just when we finish one of these loops, we found out how many boxes it took. And I want to find out on average how many boxes does it take. So we'll have a big loop, you know, n equals 1 to numDo, and then we find number of boxes to get all toys, increase counter by that, increase, you know, like the variance of the counter by square of that. So it would be something like that. And now we can calculate mean and then calculate mean by dividing by numDo. Similarly, you can get the variance from the expected value of x squared minus the square of the expected value of x squared. So again, depending on what you want to do, there's lots of ways to do the calculations. I strongly urge you to do at least one of them. So write the code, try to make sure it can work. You know, there's going to be some coding on the midterm. This is a chance to just make sure that you can code things well. Any of these approaches is fine. All right, so this is a good place to stop. And I hope no one will ever forget again to check endpoints.